Day then so far, week so far. Success so far. Yeah, success so far. Good, good, good. Getting into the swing of things. Yeah, that is that's always the goal, right? Coaching nerds, you know. Cool. Oh, were you? Okay. Have some before we get started. Okay. The first change that you'll notice here is that if you looked at the content calendar in the past, you will have noticed that the written homeworks were every week. That was incorrect. That's too much. You won't be able to do it over 2 weeks is reasonable. Because this gives you enough time to, learn the material a little bit in class, and more importantly, you'll work through some of the math outside of class, right? In class, we'll try and show a little bit of equations and maybe work through that in how the applications work. But in practice, the way that you learn how to do algebra, the way that you learn how to do calculus is by doing. So if that sounds like it sucks, sorry. No, that's cool. Okay. So we'll do it over 2 weeks. So I'll give you the first one next. All right, it's not supposed to be Wednesday, it's Thursday. Okay, next Thursday, and it'll cover basically just thermodynamics. In the perspective of how we're going to think about the interiors of planets. So today we're going to finish our discussion. I know that the very first class went a little long. We didn't get through the inventory of the solar system. So, stuff will slide around and we'll try and catch up as best we can. Questions, comments, concerns?
So for each of these homeworks, it's just gonna be the Tuesday before the homework was handed out, or is it everything up until that Tuesday?
It'll be so I'll hand it out at the end of class. So like if it was a week from today, I would hand it out at the end of this week. And it would be everything up until the time that you get it. Yeah. So I do recommend, and if you look at any of my rate my professors, very consistently, what it says is be expected to read. So not only will I expect you to obviously pay attention in class, and that's a thing that everyone here is probably very good at, considering how small the class is. You'll be doing a lot of work outside of class. And some of that will be reading. Some of that will just be like reading the material before you get here, just to see what you're going to see. But more importantly, it's going to be working through the material once you get it. And since you have 2 weeks, right, you're going to have more content, but you're also going to have more time to work through it. Right, this one should be 2 weeks. So this will be here, the 19th. There's 2 weeks to work on a 2-week material, right? So it'll be kind of out of phase, except right at the very end when you're going to get a homework and it'll be due during finals week, right? So hold on, this is the wrong date. I'll update these all. So it'll be due here at the beginning of class, and then you'll get the new one at the end of class. Does that make sense? And then here is the only one that's a little weird. So now we have 8 homeworks. And they'll cover all the topics that I put. Cool. Okay, so we're just gonna jump back into this discussion really quickly, because I obviously jumped through the heliosphere quite quickly because it's sort of the end. What was the heliosphere again? Yeah. Solar wind. Not just the solar wind, right? But it's also, the heliosphere is all of the influence of the sun.
So that is the sun's magnetic field pressing out into surrounding space. Now, it is true that the solar wind, which is the material coming off the surface of the sun at very high velocities, that's going to be streaming out along those magnetic field lines. And it's easy to think of those as the same thing, right? So they all exist within the heliosphere. Everything that you ever known and loved lives in this little dot down below there. The scales here are quite large. I can put an updated scale if we talk about this in more detail. Say that again?
That's scary.
Yeah. Yeah, right. So I mean, if you really think about what this looks like from very far away, of course you can't see any of this. It's very hard to see magnetic fields. You can only see magnetic fields interaction with matter, right? So magnetic fields themselves don't do stuff, right? They just influence stuff. The solar wind is a plasma traveling at supersonic speeds. Supersonic speeds means that you are not in the regime where the fluid is in contact with other parts of the fluid. That is to say, as soon as it interacts with material, it hits a shock. And you'll learn about that in fluid dynamics or later on in grad school, how shocks are discontinuities in the fluid. The fluid is streaming like this, and then it has a sharp boundary. And typically we think of fluids as being continuous, right? So therefore any sharp boundary would be a discontinuity in the fluid. Cool. And of course, where it interacts with the interstellar medium, that's the stuff in between stars, is called the heliopause. And you will hear this word pause. That just means stop. Stop. Yeah. Pause means stop. And in the context of these two words together, what would heliopause mean? Stop. Hold on. There's lots of folks. Someone who hasn't talked to me.
I would say it interferes with it, so like.
Okay. Okay. Good thinking about it. Yeah.
I would just say like the end of like the reach of the.
Yeah. Yeah. So that's kind of what we're thinking about, right? It's the end of that thing. So we might say, for example, the word homopause when we talk about atmospheres. Homo being the same. Homopause will be the layer in the atmosphere, the region in the atmosphere, where we go from everything being the same to everything being no longer the same. So for example, once you get above the homopause, now you have mass separation between each of the species. So lighter species are going to drift towards the top, whereas below the homopause, they're going to be well mixed. Does that make sense? Similarly here, heliopause is the effect of the sun is now paused. Right? Okay. I care a lot about words. As we become more of a technical expert, we're going to try and use that because using exactly the right word in the right context is how we become good writers. It's how we communicate effectively, right? Okay, cosmic rays are part of the heliosphere. They are affected by magnetic fields. These cosmic rays do not come from the sun primarily, hence the word cosmic. Very good, yeah, right. Okay, so they're cosmic. So they come from the cosmos. And you'll notice that they come from lots of different directions. Cosmic rays are sometimes hinted at as the reason for thunderstorms. To talk about when we talk about atmospheres. Our thunderstorms, yeah.
Is it just in regards to just our planet or like different planets as well?
All thunderstorms.
And you'll understand why that is when we talk about why thunderstorms are weird. Because you should be surprised that thunder exists, but you don't realize that you're surprised about it. Yeah, right. Because you see it, it's just fucking there. So of course it exists. Okay. So let's go. I skipped through a couple things here. In almost all stellar systems, that is to say those outside of our sun, all you know about is the stars. So similar like we said about the sun, that's the only thing you see, right? That's the luminosity. We don't see Jupiter if you are many, many light years away, not even with the best telescopes. You see the influence of Jupiter on the star. And we can talk about all the ways in which we detect exoplanets. The only time that we see individual planets is when they're quite far from their parent star. And of course, the Earth is quite close, thankfully, because that's why we're nice and warm. Right? Okay. They have surprising properties. We'll talk about like high eccentricity stars, small radii from the star, like that is to say very close to the star, small, I should maybe put small to maybe Draxus. Yeah, this is really telling us that the circumstances under which our solar system evolved are likely the exception, which is kind of surprising. So majority of the systems that we see are not like the ones that, sorry, the majority of phenomena that we see here are not the majority of phenomena that we see in all other systems. And as a philosophical point of view, you can take this to mean, well, of course. So there's something called the anthropomorphic interpretation, which is life exists with characteristics such that life could exist. What I mean by that is, of course, we are at a distance where liquid water is available here, because if we were at a different distance, then life would not have arrived, right? So we happen to be at a place where you have liquid water on the surface. That does not mean because we are at a place with liquid water on the surface that it's common. Does that make sense? Okay, so that's a really important distinction when we start looking at other solar systems. And we'll talk about how, through the history of understanding the solar system, we thought in the first one, which is that this is the way that the architecture of solar systems must be constructed, because this is what we have access to. And with new information, of course, we would have to revise those theories. The one you see in the background is, you can't really see it here. Can you sort of that? But this is its parent star of HD 209458, and then its closest planet. We'll talk about that as well. Exoplanet power. No one knows exoplanet power. Oh, you got a couple Keplers? That's good. Okay. So now let's go back into talking about what are the direct observables. And I think we had a couple. I apologize, it's a really shitty marker. What were the ones we talked about? Composition. Okay, it sucks, I know. I'll run downstairs. What else? Nice, very good. Ratings, very good.
Oh, okay.
Oh, you can't do two, now you just stole one. Alright, you did, oh,
Oh,
yeah,
that's
sorry. Rotation. Alright, who hasn't gone yet? Distance. Distance. Yeah, good. Distance from what? Distance from what? From us? Does that matter in understanding? I mean, you could absolutely do that, right?
Yeah.
But what's the important part? Distance from star.
Yeah.
Which is another way, of course, of saying distance from us, because you want to know how far that star is. But really what you care about is how far is that planet away from its star, right? And of course, in our solar system, we care deeply about that, because we think of it in the context of, say, something warm. So if you're close, it's hot. If you're far, it's cold. Campfire, right? So distance. Oh my. All right, that's unacceptable. Okay, what else? Yeah. Good. Okay. What does that do? How do we measure that?
Like light years, like looking at its sun.
Okay, good. And how is it different from rotation?
See rotation, sorry.
No. This is important.
Yeah,
What's the difference between rotation and orbital period?
orbital period is how it rotates around the star, whereas like rotation is its own rotation.
Good. Yeah. So rotation would be internal rotation, which tells you something about day-night changes of heat and cold. Whereas orbital period, in particular, if we think about, say, other orbital properties, like for example, is orbital period important if you have no eccentricity? What's eccentricity? A circular orbit. So for example, if we think of it like a comet orbit, you spend most of your time very far away from the star, and then you come in, and let's say that's a 1,000,000-year orbit. Is that going to be very different for the planet than if you say have a 1,000,000-year orbit where you spend almost no time near the star. It's Sergio. You don't think so? You come in very close to the star and you spend a lot of time out. When you come in, be very different. The reason for that is that you get closer, like we said, at the distance, you're gonna get hot. So let's say you spend a lot of time out here, okay, that's all great, but every 1,000,000 years you come in and absolutely scorch the surface and maybe blow off any atmosphere, right? And we'll talk about the implications like this. Okay, so not just distance, that's gonna be related to orbit, and also eccentricity. Right? Anything else?
More.
There's more.
Um, the albedo plant.
Albedo, good, what does that mean?
How much light?
Right. And what's a typical albedo?
Snow.
What would that mean? What does that mean?
That was one.
No, one? Okay, black body would be something that absorbs all light. Snow would be a perfect reflector, that would be one, but I don't think any snow is really one. Right? We get close, like 0.9 is very good. But one would be not a single piece of light gets absorbed. And of course, we know snow melts. Right? Okay, so it's, it's close to one is great. I don't know exactly what the fraction is, but this goes between 0 and 1. And what are rocks? Right, it's closer to 1. Okay. Anything else? We got one of them so far. You're missing a big one. Yeah. What does that tell you? Okay. Sorry. Let's think about like what are so we're talking about physical properties that we can determine
Could it be like velocity?
of the planet itself. We're not thinking about the star anymore. You could absolutely do luminosity, but we talked about that last time about how the only thing that is luminous on its own power is Jupiter. And it's very, very dim. So we can certainly observe it here, but there's a more fundamental question that we might want to know when we directly observe something. Consider for a moment that we're on the Earth. So Earth could be included in that. And there's a very fundamental property about the Earth that you're missing so far. What?
Let's data map. Remember.
The atmosphere?
Okay, there's a couple things there. Are these things that can be directly observed? You're using things that we'll talk about certainly in the course of this class. But what's the thing that you observe? So you said habitability. That'll require knowing things like whether it has an atmosphere, what the temperature is, and then we'll have to make inferences, right? So that's not the direct observability. We have composition here, right? So that's telling you the composition potentially of the atmosphere itself, if there is one, right? So atmo and surface, right? If it has one.
Is it surface features like cratering and such like that?
Right, if it has one, right? It has them. Right, so you can get morphology from that. We need a more fundamental measurement. Size. Right there.
Oh.
Anyone here can drink? Can everyone drink? Oh, the age. Oh, that's important, right?
Oh my god. Okay, so age is in there. What else? So we had mass. There's one that you haven't noticed yet, which is how is the mass distributed? And that's really important. And we'll talk about why that's really important, because how the mass is distributed tells you about the interior of the planet. So far, we've thought and talked a lot about the exterior. What does the surface look like? Are there surface processes? But very important to know is if the mass is distributed in one way versus another, this might tell us whether we have a core, whether it's liquid, whether there's subsurface oceans, etc. Right? Okay, next one we had size. Okay, everyone got that. We had rotation rate. One we missed there was the spin axis. Is it straight up and down? Is it tilted to the side so that you have seasons? Is it flipped completely 180 so that it's rotating backwards? Right, like Venus? Is it tipped on its side so that it's showing a weird part the whole time with like Uranus? Shape. No one cared about shape. No one even loves shape. Right? Is the planet weird and wonky? Is it lumpy like my head? Right? Temperature, I would take temperature. That was someone said that earlier. I would take that. We didn't put it up on the wall. Magnetic field. Is there one? Can we measure it? Is it present? Can you measure magnetic fields? Yeah. How do you do that? That's correct. Yeah, all you have to do is take the word right, thermometer, magnet, magnetometer, done. And in fact, magnetometers are very cheap and they're very easy to fly. The only thing that's tricky is that, they can be small. So for example, they can be about the size of a quarter, but you usually need to place them far away on your spacecraft because they want to be out away from where, all your electronics are producing their own magnetic field, at least close. And if it's nice and far away, then you can delete the spacecraft and just measure whatever you're measuring out there. Okay. Okay. Anything else? Well, obviously, there's more space, right? Surface composition, we said that one. Surface morphology, said that one. And then together, atmospheric structure and composition. Okay. Questions, comments, concerns? Okay. So, what are the properties that can be inferred or modeled from those properties that we just talked about? Yeah, what can we learn based on those things that we said? Find out stuff about the interior, sure. And what are some, let's say we combine some of these things that we can measure directly, right? Like these are things that we can actually measure. So we do composition, we say there's 30% hydrogen in the atmosphere. Okay. We can do things like say the mass, I weighed the thing and it was 2 Earth masses. We get the radius and it's 1.5 Earth radius. So now what can we do with that information? What properties can we infer?
Can you find the density?
Perfect, right? You want to know the density because that will tell us what? I might infer the composition, right? The interior composition. So if I told you that the bulk density of the object is less than 3 grams per cubic centimeter, what does that mean? There is a geologic answer for it, right? So rocks are approximately what density in grams per cubic centimeter? 3 to 3. Yeah, 3 to 3.5. Maybe if you want to get a little like metally in there, you can bring it up to 5 and someone will still believe you. What about ice? What? 1 is a very good approximation. It's about 0.9 because ice likes to make space. Water is 1, but if you said 1 or 0.9, that's the same answer in this class, right? Okay, so if I tell you that the density is 2, what does that tell you?
Or it's split.
Maybe. Just tells you that it's less dense than rock. Right?
It's the one.
Because, and we'll see this, the ice giants have a density less than 3. But they're certainly not rock. Right? They're a mixture. But what this tells us is that it's not a terrestrial planet. So if I tell you that the density of Mercury is 5, you know right away, okay, that's a terrestrial planet. Right? Okay, and there's a little bit more ambiguity. You know, for example, Saturn might be 0.6. Like, what the fuck? That's less dense than water? How do you make something less dense than water? Well, of course, you use hydrogen, helium, right? Okay. Anything else?
Radius and the shape of it, we can infer differentiation.
Yeah, exactly right. So we can think about the density and function and temperature as a function of position. We can look at how the surface will heat throughout the orbit and due to the rotation. We can think about what the atmosphere does to redistribute heat, for example. We can think about the formation. That is, you can get it from the age, you can get it from the composition, right? You can think about whether or not it must have formed in the location that you see it. Okay, so for example, if you look at the composition of stuff nearby and you say, hey, this thing doesn't look like anything that it formed nearby. Well, chances are it came from somewhere else, right? Okay. You can think about the geological history. What did it go through? So you look at the surface of the moon and you look at the morphology on the surface and you say there are lots of craters. So it must have been hit. That's it, right? So there you go. That's inferring the geologic history of the moon. Now we can, of course, do better than that by looking at the composition and finding out when it was hit. And we can talk about impact cratering in more detail, right? But that's how we start. We can think about the dynamical history, and we'll talk about how you can get that type of work from understanding the orbit itself. Okay? Okay. So let's start by understanding how we can use this information and modern techniques in order to even determine stuff about the Earth, right? So the first part we're going to talk about today is how do we know? We're going to look at direct evidence. Okay, so in 2300, or if you took an astro class outside, you know, not with me, you may have just heard, well, just believe me, right? Whatever. I'm going to try and show you the evidence in as close a way as we can. Some ways, you know, you'll have to believe me because we don't have enough time to go into all of it. But I would love for you to get the sensation of being like, oh, this is the frames that I would use in order to understand it better. Okay. So let's talk about the Earth is approximately spherical. Do you agree on it? All right, it's a direct observation. We can see it. Okay, it's been known since about 500 years before Christ. That's about 2,500 years ago. Okay, here's a picture. This is a composite image. You take a picture of the lunar eclipse. You keep taking photos, and then you stitch them together. And of course, this is the shadow of the Earth projected onto the moon. As the moon passes behind the Earth's shadow, you can see it draw out the fact that it is curved. So you can tell that the lunar phases indicates that the moon, shines by reflected sunlight. Right, that's the first thing you have to determine, is that based on its orientation around us, we can tell that, okay, it's illuminated here in, say, something like a quarter phase. Whatever. If I put it here, maybe that's a crescent phase, and then if I put it in front, you look a new phase. Right? So that's the first thing we do. And therefore we say that the full moon is nearly on the opposite side of the sky. Fully here, and the light's coming from behind me. Right? Okay, full, boom, right? And then when it passes, oh god, in front of me, when it passes in front of my face, right? You can see the curve of my brain, right? You see that? You see the picture? All right, good. All right.
So we can see it. And therefore the lunar eclipses of the Earth's shadow are cast on the moon. Since the edge of the shadow is always circular, right? This isn't the only time people have seen it. Every time there's a lunar eclipse, it's always circular. It's not like one time there's like a slit from like the fact that the Earth is like edge on, right? So in fact, we must infer that it's in fact circular. It's your question. Good. What about this one? The planets all orbit the sun. And they lie nearly in the same plane. This is also a direct observation. Of course, we see that the planets and the sun lie in a band called the zodiac. Right? This has obviously led to some interesting interpretation in modern times. But this is the plane of the ecliptic where the sun travels. And we see the planets travel in those same regions. Of course, planet means in Greek, wandering star. So these were the first observations where people said, I go out there every night and this star seems to move across the night sky. And they noticed that it moved similar to how the sun moved across the sky. So the sun would go across like that, and then they'd watch at night, and it would follow in that same plane. They never left the plane, right? Or if they left the plane, there were small deviations. So that's the idea that the planets lie in a plane, edge on, that we probably lie in as well. We also notice that distant stars, right, in the direction of the zodiac, so as we travel around it, we notice wiggles, right, in their wavelengths. That's the Doppler effect. So as we move towards it, the light that they are emitting gets blue shifted or red shifted? Blue shift, so it becomes higher frequency. So this is like when the fire engine is coming towards you and it's high pitched. And then as we move away from it, it gets lower. And what's that called? It said blue shifted, so it must be red shifted. Good. Okay, we want to know all the words, right? So that lower frequency sounds like the woo as it drives away, right? And we watch that wobble, right? Okay. So we can tell how fast we are going. And we're going about 30 kilometers per second around the sun. So the Earth travels in approximately a circular path at 30 kilometers per second, centered on the sun. And we can do this by looking all around at different stars. If we were in an elliptical orbit, okay, let's draw this really quickly. Here's our sun. Really good drawing of the sun. Don't even think about it. Okay. And then, horrifying. Okay, here's our really good elliptical drawing. Okay, right? Where am I going the fastest? Nearest the sun, at something called, correct, perihelion. So this location is perihelion. And I'm going, right? Where am I going the slowest? Aphelion. And V is down. So if I took a measurement here, right, and I look at some distant stars, I take the rate. Oh God, this is a nightmare. And I take a distant measurement of stars at perihelion versus aphelion, and I found that I was going like twice as fast at perihelion versus aphelion, then I would conclude that the orbit was elliptical. But since it's 30 basically the whole time, we're pretty close to, sorry, you see, direct measurements to demonstrate. Okay. Here's the Doppler effect. You familiar with it? No. Okay. You have two light emitters and detectors that can measure wavelength very accurately. You have to be moving along the line of sight. So for example, if I'm headed in this direction, right, then Zori, in fact, will not see any Doppler shift because we are in tangent directions. So it's only compression along the line of direction. And you can think about this exactly the way that you think about a fire truck. Because as every pulse or blare of the siren goes, as it moves towards you, it's moving with the wave. And so it compresses the fronts of that wave to make the pitch higher. That is to say, the time between peaks becomes artificially shortened. Now, if you look at it from the side, there's no difference, right? Because as the wave hits you, it's going to hit you at each one of those. As it passes by you, you hear it at the normal pitch. And then as it goes away from you, then it's lengthened again. Okay? And so this is the map for it. So you can take the wavelength here, you can measure it, and this would be the rest wavelength, the one that you see at zero velocity. Lambda naught. The lambda naught is the rest velocity. And you can see this as a beautiful formula. 1 plus v over c. What can v be? Right, what are the largest and smallest values v can be?
0, 1, 2, 3.
In magnitude, yes. Yeah, very good. So in magnitude, you can go from 0 to c. What's the smallest it can be? This is not a trick question. B minus c. Right? So you can be going away from you. So we have a range here, right? Because this could obviously go, this could be 1 plus 0, right? Or it could be 1 minus 1, right? Which would be 0, right? Thankfully, nothing moves at the speed of light. Or it could be 1 plus 1 is 2. All right, we get it, right? So the Doppler effect is going back and forth. You have some central line. Let's say you have an emission that occurs at 121 nanometers. You'll watch it move back and forth, and back and forth, and back and forth. That is telling you the motion of the current. Right? Okay. You won't learn why, because you're not going to take EM, but maybe some of you will. Okay, who's in EM? 1, 2. You gonna take it?
I'm not sure.
Oh, you should. It's fun.
I'll probably take it in grass.
Yeah, sure. Okay. So what about this one? How do we know the AU, astronomical unit? We just go out there with rulers? No, sorry, you don't go out there with rulers? What do we do?
The average is 7.
That's the definition. How do we measure? Using what? Go back to basics. V equals speed of light over distance over time. Good. How do I measure a distance? V times t. Okay. So V times t equals the distance. And now, how do I measure the distance to the sun?
Use the speed of light multiplied by how long it takes to spread it from the sun to right here to Earth.
Okay, good. So you're almost there. There's 80% there, but I can't tell when the sun decided to do a thing. So I can, for example, turn on a light, and let's say it's a radar light, and I can pulse the radar. I can bounce it off of things that are hard. So bouncing it off the earth is actually easy, hard, bounces, goes right up. Bouncing off the moon is also really hard. Bouncing off the sun is impossible. The sun is just gonna eat it up, right? So we use this exact property, but we're gonna use it on other planets. Okay, and in fact, using it on Mercury or Venus gives the most accurate results. Okay, so how do you do this? Well, you wait. So, for example, if the sun is here, in this beautiful picture that I did not draw, it's another drawer, and here's the Earth, you can measure the angle between them. And then you bounce a radar pulse, boom, boom, and you measure this distance d. And by the wonders of geometry, okay, we can get this one. Ta-da! Simple, right? So you want to do a couple things here. You want to make sure that the line of sight is perpendicular to Venus. So you get a nice bounce back. Bing. And you don't want it to be like real here. You don't get a very good measure. And of course, we can measure it the whole time, let it go around, see if it has these interesting differences or anything like that. Okay. Cool. Questions about this? Okay. How do we know that the solar system is approximately 4.6 something billion years old? Excuse me? Good. What kind of chemical analysis? Very good. All right. So this is like we have some nice variety of folks who know stuff, right? And as a geologist, we know that we can radiometrically date rocks. Okay. That's not you going and having a special time with the rock. That's finding out what the interior of the rock's composition has done in the past, however long it's taken to crystallize, right? So the properties of a rock are set when it crystallizes. And then things change. So you can't tell, for example, what the rock did before crystallization, unless you can tell something about the region that it came. So for example, we can know about the protoplanetary disk, that is to say where rocks crystallize from. But if you had some little pieces in the protoplanetary disk, and then they were brought into a planet and melted in the interior of the planet, they now have lost all of the compositional information about their pre-accretion history. Does that make sense? And you have to use stuff from the disk in order to understand the disk. You can't use stuff from the interior of the Earth because that's been heated. Right? Okay. We'll look through this. It says great detail. That might be exaggeration. Because I like rocks a little bit. I'm not great at rocks. We'll talk about this in the context of how we can understand composition and metamorphic history of rocks for terrestrial surfaces. Right? What does that tell us about terrestrial life surfaces? Okay, obviously, we don't get to do this with the icy moons of Jupiter, because we have not yet gone them up. But soon, right? Okay. So when rocks melt, the contents homogenize pretty thoroughly. Right? You just get everything all mixed together. They recrystallize as they cool off, and then you're going to have fractions of trace impurities. And sometimes you're hoping that the trace impurities are radioactive. Right? So depending on which radioactive element you love, you might be able to do different types of dating. So if you have something that's really long-lived, then you can measure, for example, the abundance of one group of mineral or one group of elements to its radioactive counterpart, the daughter versus the parent nuclei, right? And that gives you something like the age of the rock. Okay. The oldest rocks in the solar system are 4.567 billion years old. We cannot find any rocks in the solar system older. Where do you find them? Yeah, where do you find them? Where's that again? Comets and asteroids. Good. Can you find them on the Earth? No, why not? Because they melted. And another way of saying that is that the Earth formed after them. Right? Okay, so necessarily, when the Earth formed, as we said before, when rocks melt, the contents homogenize. So we can get the oldest rocks on Earth, and that's pretty cool, but it's not the oldest rocks that exist. Right? Cool. And we'll talk about that in some detail. Okay, here's a facts. There's a nice little fact sheet if you go onto the Astro 33, or sorry, the Canvas 3300 page. It has like an information and it has all these numbers and it has some stuff that I'm going to show you next. So here's your water ice. I said 0.9, so that was wrong. My bad. 4. And here's water. And these are your units of CC. And these are the ones I want you to sort of like have in the back of your mind. I'm going to say them a lot. You're going to learn them Carbonaceous minerals are about 2.5, silicate minerals are 3.5. So 3 is fine. Okay. Iron is 5. Right, remember that as astronomers, we're just gonna wave our hands in some perspective, right? So, iron sulfide is 5. Iron itself is. Okay. These you probably never need to have memorized. Because we won't use them, but you should have them ready to go. If you like Wolfram Alpha, you can type them in there as well. The ones that do matter are over here, of course. This is 3 times 10 to the 10 cubic centimeters for speed of light. Earth mass is 6 times 10 to the 27 grams. And if you want, we can do this in terms of 6,400 kilometers. You see that? That's right. Pretty good. And the day, wow, come on now, let's not be assholes. The day is the day, but the sidereal year is not the same, of course, as the year that we're used to. That's why we have leap years. Solar mass, solar radius. We can think about these in terms of the standard units, GM and CM, but I will kind of interchangeably use like, okay, the Earth is 1/3000 or whatever the unit is. Solar temperature, we're going to be in Kelvin, basically the whole time. Okay. Solar luminosities, that's fine. Apparent magnitude, you fill with the magnitude system for brightness. So if you go out tonight and you want to look at, say, Vega, that's like a 4th or 5th magnitude star. Okay. And as you go between 4 and 5 magnitudes, there is a factor of 10 difference between the brightness. What is brighter? Smaller numbers or bigger numbers? Smaller numbers, counterintuitively, very annoying. Okay. And so if I say -26, that's a really, really small number. Right? Yeah, I prepped you for thinking about it with C. Small. Okay. Light year, fine. Parsec, whatever. Cool. Sidereal is the idea that as I go around, coming back to the same place. Okay. Showing the same face of the sun. And I'll show you a diagram of that. Here's some more. Oh, it sucks. But look, there's a lot of stuff that we wanted in here, right? We have the semi-major axis, right? Cool, we can measure that. We have the revolution, or how long it takes to go around the sun. We have eccentricity, E. Okay, that's fun. We got how long it rotates, how quickly it rotates. Okay? And we have that in days. Thank God. Seconds would fucking kill us. Radius, big kilometers. Mass, okay. So we have some weird ones in here. And albedo. So close your eyes, don't look. Yeah, do you have a question?
The negative in front of you, is that because it's backwards? Rotating backwards.
And close your eyes. You're all looking at it. You're studying it now, and I'm trying to quiz you on it. Close your eyes. Okay. What is the most reflective planet? Raise your hand. Yeah, what you got here? Jupiter. What do you think? Your eyes? Ah! Yeah, visual albedo. So remember the albedo is the reflectivity. It goes between 0 and 1, right? Okay. Who's the most reflective planet? What's that? How do you say this? Uranus is 5 to 6. No, 6. Yes, 6. That's fine. Cool. Venus has a lot of really fun stuff about it. We'll talk about how the total amount of light that we get from Venus does not change throughout the year. That should be very surprising to you because Venus moves away from us and it moves towards us. Why does the amount of light that gives us not change.
Because since it's so reflective, the sun is giving that light.
Well, yeah, it's definitely scattering light from the sun. But what about Venus is changing as it goes around the sun? Not really, not so much. It is true, the exterior of it is quite warm, right? That is not the primary reason why we see the same amount of light. So for example, if I had a candle and I walked away from you, you would see the light get dimmer. And if I brought it back to you, you'd see it get brighter or flash. That's not exactly what's happening in the forest, right?
Yeah, it's really slow.
Nothing to do with rotation. Something to do with how we see it, the geometry. Backward. Okay. Put a picture on it. Okay, there. What changes throughout the year when we look at it? The distance, obviously, but what else? For that. Angle certainly is changing, what do you mean by that?
Say that as the distance changes, the angle changes, it's always reflecting perpendicularly towards us.
Well, like what if it's here? And the light goes here and the fountain, so that's not quite. Yeah, we'll figure it out.
You better. Okay. So today we're going to talk about energy transport and the temperatures of planets. We're going to try, we probably won't get through all of this. We only have like 20 minutes, 25 minutes. We're going to talk about heat conduction and internal heat generation. We'll try to talk about the internal temperatures of rocky planets. And then we try to get into the idea of how small could a differentiated body. Does that make sense? What is a differentiated body?
Someone who's interior slowly.
It doesn't have to do that. Right? You can have warm interiors. What is the word differentiated?
Like changing.
That would be like a differential, sure, like a change, like a rate of change. Differentiated would be the past tense of that. Interior change, good, right? Differentiated means interior change. And in this particular circumstance, when I say the word differentiated, I mean what about the interior change? Sure, heat definitely will have changed, sure. But that's not what the word differentiated means.
Oh,
Yeah.
like,
Sorry, go ahead.
oh, it's like, so like what stuff had like the same towards Victoria and what stuff had.
Exactly. So differentiated means that we have mass differences. In the center, heavy. On the exterior, not heavy, light. If you start off with just a clump, go outside tonight, that's a bad idea. But if you had like a clump of mud, and you just grabbed it from a stream, you might have big rocks in there and small rocks in there and mud and whatever else. If you held it for long enough, the rocks would sink to the bottom and the mud would end up on top. That would be the process of differentiation. Right? And if you shake it up, maybe they're all going mixed up. So you can think about early planetesimals, things that make the planets, as being shaped up. And you gotta wait for stuff to move to the middle. If it's not hot enough, it will not move towards the middle because rocks support other rocks. If it's magma, certainly get differentiation. Right? Okay. Here's an image. Ow. Okay, that was fine. Here's an image of the exterior of Mars. This is surface temperatures. And what's this thing on the very top? Polarized. Cold. Yeah, good. We like that. You can tell it's cold because blue. Even though for stars we use the opposite, right? Well, for stars, bluer stars are hotter, right? And of course, for everything, if this is a flame, which one's the one that you don't want to touch? The blue one. I want to touch the red one, but human beings are stupid and we. Red means danger, right? So red means blood, so we thought red meant hot, even though it means blue. Okay. All right, let's talk about the definition of a planet. This is stolen from Wikipedia. But of course, it's not stolen from Wikipedia because it is written by the 2006 definition. What is the definition of planet? Excuse me? It is very conditioned to be a planet.
Its orbit has to be like flat.
Excuse me?
Its orbit has to be like flat,
What do you mean flat?
like in a disk.
Okay, yeah, so you orbit within the disk, okay.
You work's gotta be clear.
Spirited debris, okay, all right,
Has to be like a certain size.
okay, what size? What?
Is it bigger than Pluto?
Pluto, no, incorrect. So Pluto did not lose it because of its size. And size is close, but we kind of use this word interchangeably. Because size, large enough size means that you're gonna have a different property. If you're large enough, then you will become spherical. Right? If you're not large enough, then you don't have enough mass to turn you look like a lumpy potato. Right? So the first word that we really want there is the shape. Okay, so it needs to be in orbit around the sun. And this is slightly different than what you mentioned, because actually there's no restrictions on it being in the plane. But it can't orbit another body. So this automatically excludes all moons. Right? So using this definition, all satellites that are not going around the sun, they're out. Okay, so you say, well, we can make our own planet. Let's just build something and we'll put it into orbit around the sun. Well, no, that's immediately wrong because it needs to have sufficient mass to create hydrostatic equilibrium. What does that mean?
Nearly around.
Good, that's not what the word hydrostatic equilibrium means, right? What does hydrostatic equilibrium mean?
I think of water.
Right, yeah. So this could be a little, this choice of these two words is a historic choice. Hydrostatic equilibrium, of course, being the description of the atmosphere. But we can use this for any body that's fluid. For example, the Earth has fluid in its interior. So hydrostatic equilibrium is the description that gravity is balanced against pressure. Okay. So currently, I am in hydrostatic equilibrium with the floor. I am not going through the floor. Okay. In this particular circumstance, we have hydrostatic equilibrium that creates a nearly round shape. This is not always the case because for certain fast rotators, you can have oblateness, like there's rounder right at the top. Okay, they're spinning very fast, poles are coming down. Okay. And then, of course, the one that Pluto lost didn't clean up after his neighbors. Right? So if you gobble up all your competition, you get to be a planet. So Pluto does both of these. It is large enough that it's circular, right? It's got this really nice shape to it. It's going around the sun. Kind of. It's kind of going around its friend, but it's got too many friends. It's got 4 other friends that are comparable in size. So it didn't do a good job of eating. Okay. All right. I'm going to do that forever. All right. Let's talk about energy transport in planets. In the interior is where we're going to start. But these concepts will, of course, be used again when we think about the transport of fluids in atmospheres. So first, let's think about these 3 processes: conduction, radiation, or convection. Give me an example of conduction. What? That is conduction of electricity. That's correct, but I want convection of heat.
Or else I think.
That is radiation.
So magnetic fields.
That would be magnetic fields.
Metals can transfer much as this, or not as much, but metals are a good conductor of heat as well.
That's true. Good. So what do we mean by that? We say heat conducts. What? Sure, but let's think just about solids for a moment. We want to think about the interior of planets. There's 3 ways to get heat in the interior of a planet. Yeah, but that's not one of these 3 processes. Okay. Have you ever touched a hot stove? Which one of these is that? Conduction. Your skin conducts heat. The thing was hot. You pressed it. Heat went into your body. It may burn. Ow. Oh. Okay. That's conduction. What's radiation? 95 degrees Celsius. So you can get close, and you got some warning signs because you're getting infrared waves that are heating your hand. Good. What's the third one? It's good. And an example of that would be in your day-to-day life.
Heat rises, cold sinks.
Heat rises, cold sinks. Good. So let's cook, right? Let's make some soup, like miso soup makes these little cells in it, where hot material flows upwards, cools, and then sinks. And you can see those cells, and they will look identical to cells in the convecting surface of the sun. Or if you go home and you want to make a little turkey, okay, you turn on, it says convective bake. It's circulating air that heats from the bottom, goes up, heats your food, cools down, gets heated. Convection. Cool. All right. The transported solid is almost always dominated by conduction. Radiation dominates in space and through tenuous gases, a little bit through atmospheres. Convection and radiation are important in the interior of stars, planetary atmospheres, and their cores. But sometimes you also get conduction, depending on how big the object is. And conduction is most applicable in terrestrial planet interiors. Okay. Okay. About to look at math. Whew. All right. Heat conduction is the transport of energy by collisions. You have particles, they bounce into each other, and they transfer kinetic energy. But it's an aggregate, of course, right? So as I bring my hand, which is a collection of atoms and molecules, into contact with something hot, those with lots of energy in the hot object then start hitting my hand and making them move quickly, which is our sensation of heat, right? And we can talk about something like the heat flux, Ft. How much heat flows through a cubic centimeter, or sorry, a square centimeter. So if, for example, I think about this surface here, right, as my test surface, how many particles of heat are coming through it? Right, that's the first centimeter. And here's the seconds. So this is a rate. And the unit here is erg. Now, erg is just, we can go back to the SI units, that's easier. But usually we talk about heat flow in that way. Does that make sense? The rate of heat flow is a radiation. Okay. So if you talk about 2 planar uniform temperature surfaces, which we draw better right now, but let's imagine that you have something that looks like that. And this has some temperature T1. And you have some separation between another object, T2. And that separation here is dz, some infinitesimal separation. Okay? And the difference between dt1 and dt2
is dt. Right? So think about it like layers in cake or layers in an onion. Small separated distances, right? Okay. As long as the median separating the planes is uniform, you don't get like different types of onions as you go. And as long as it's all the same type of onion, then the heat flux is given by this. Okay, that kappa, this is the diffusivity of heat, and this is the rate of change of heat as a function of distance. What does that mean? What does heat flow mean? Okay, so if I have, for example, hot over here and cold over here, let's think about that in the context of calculus. What is the slope look like? dt dz.
Your friend
They're not brand new, are they?
is there.
No, it did to me. Okay. Okay. Here's T. Here's Z. Here's Z1. Here's Z2. Okay, this point here, it's hot or it's cold. This point here, it's hot. They're separated by some distance, dz. They have some difference in temperature, dt. What do you expect to happen to these 2 points that are in contact? The physical system, 2 objects touching each other, one's hot, one's cold.
Equilibrium.
They equal out, right? The hot one will become cooler and the cooler one will become good. Okay, that's the physical intuition that we need to start with. Now, mathematically, does that make sense based on what I wrote? So let's look at the slope in TdZ. In TdZ, what does that mean? We know calculus, right? So what is dTdZ? The derivative of t with respect to c, which is a rate of change or a slope. What's the slope? What? Yeah, in this particular circumstance, it's going to be linear between the 2 objects. Oh, fuck, that was a bad drawing. Okay. Okay, but it's also that between point A and point B.
So it's a linear growth.
No, hold on, let's not get ahead of ourselves. Okay, just because we have 2 points doesn't mean it's linear. It's a slope. It's a slope at a point, right? The definition of derivative is slope at a point, and it can change. It can go up and down depending on how the material is distributed. But the important thing is this positive or negative?
Positive.
This is positive. Good. So let's have a look here. It says dTdZ is a positive quantity. This is going to be a constant times a negative. Oh, interesting. So the heat flux in a positive slope is negative. What does that mean? Which direction does the heat flow?
Down.
Yeah, from hot to cold, right? So if it's going from cold to hot in the Z direction, then the flow goes backwards. That's what we expect to happen. This will come down. This will come up because the heat flow is in the minus dz direction. Right? Okay. So we're going to remember that math, shitty and sucky as it is a language. Right? And we're going to go back to thinking about calculus. I know it's been a little while. So we may have seen and used it as much as we will here. But we need to think of them in terms of this is a language that tells us how this heat flow actually works. Think in terms of slopes, think in terms of integrals, stuff like that. Okay. Okay. heat conduction in 3 dimensions, we use the gradient. That's just the dz, dx, dy, right? Okay, and in particular, we're gonna be using a lot of spherical coordinates because planets really tend to be spherical to the first approximation. And because you have spherical symmetry, that is to say, nothing changes in azimuthal or in the axial direction. You just have to think about how it changes with radius. So hot in the middle, cool at the exterior, right? Okay, and that's fine. So we can just use that. And here's some common conductivities. So quartz is 3, basaltic rock is 4.5, and stainless steel is 16. So let's hold on for a minute. Let's think about what that means in your head. The conductivity. Okay. Would you like to cook with a pan made of quartz? Why not? It would cook really slowly, right? You'd have to wait forever to fucking heat that thing up. But stainless steel is great, right? Okay. Would you like to live in a house made of quartz? Yeah, on a hot day, it would take a long time to heat up, right? Okay, would you like to live in a house made of stainless steel? On your roast, right? That basically could go right there. Okay, good. Oh, we didn't discuss that yet. I moved some of these around. So we're going to talk about accretion heating and radioactive heating. We're going to do these in opposite order. First, we're going to talk about radioactive heating. And we're going to talk about this in the context of where does the heat in the interior of the planet come from. So there's 3 sources of heat that we will discuss. If you think about like, okay, you have magma underneath the planet, right? Why is it warm?
Because the heat had escaped, it gets trapped.
Yeah, so it's very slowly escaping, that's true. But is there new heat being generated, or is it old heat from when all of the things smushed together in the first place? You think there's new heat? Okay. You think there's new heat? There's new heat? Yeah. What's the source of the new heat? I know you. Okay, so differentiation is a source of heating. That's good. So as heavy things sink, they, just for example, if I were to drop something heavy, you could crater the ground. You'd also heat it up, right? The same thing is true, for example, when masses of air fall, they can gain kinetic energy in their interior and warm up. So that's sort of a weird thing, right? As material falls throughout the interior of a planet, it can heat up as well, right? That's a source of heating, differentiation heat. Is that the only source of heat in the interior of the planet? No. What's the source of heat at the center? The core? Why is the core hot?
Radioactive.
It has to be radioactive decay. That's right. Okay, which is radioactive decay, Garrett?
Let's say we had isotopes into,
Do you know which one?
let's say,
Ooh, uranium's too long.
radium potassium.
Potassium's not abundant enough. Those are good ones though. It's aluminum. Isn't that weird?
That was not really my top 10.
Yeah, I know, right? Okay, well, let me show you really quickly here. Because I'm not gonna be able to do this all today. Come on. Oh, I thought that put it in here. No. Okay, well, we'll talk about that more, but I'll reorganize these slides for Tuesday. Because we want to talk, I think, in more detail about what the sources of heating are and why we know that there's very little accretion heating left over. So for example, when you first smush everything together, you get accretion heating. And then the stuff sinks, that's differentiation heating. And then the radioactive stuff that's the heaviest at the bottom, that's the. Okay, questions, comments, concerns?
Let me chapter 3.
Yeah, so let's have a look at what we have here. This should be in the thermodynamics section. I think it is chapter 3, but let me just double check. Yeah, the 3. And we'll talk a little about chapter 6, like mineralogy and petrology and planetary interiors. So if you start browsing through those and you're like, hey, that's kind of what we went over in class, that's perfectly okay, right? Don't feel like you have to stick to the entire chapter of thermodynamics, because as far as I recall, thermodynamics will also include, for example, entropy discussions like that. That's not always what we want. We want to look for the stuff that we've already hit on, and some of the stuff that we're going to hit on, which is accretion, radioactivity, radioactive dating, right? Okay.
Supposed to be /gen.
Yes, absolutely. And I apologize because the very first time we did this, the recording didn't record. So hopefully this time it works. I don't see, oh, it says pause recording.